Welcome to our final analysis of waves using the operation of a slab waveguide as our example. Let's set things up. This is a basic configuration of what's called a dielectric slab waveguide. You see that above and below the guide there are two dielectric materials. They're the same and they are with index refraction N1. In the middle, if you like, think of it as a sandwich, are two parallel plates or boundaries between N2 and N1. So we're only considering a parallel slab waveguide where we're not looking at the sides. So it's not a rectangle, it's basically an interface, N2 sandwiched between N1 and N1. Now, the electric field is trapped. We're in the total internal reflection mode, or angles greater than total internal reflection. We want to see what the conditions are that a wave can propagate down the guide. So let's see what happens. You can see on the diagram the wavefront AD. The wavefront AD, you can see we could start at A, go down to B, go up to C, and back to D. So in order to get stuff going down the guide, there must be constructive interference. So what we're going to do is set up the condition for constructive interference. To do that, we have to compute the total phase, going from A all the way to D, as I've just shown. Now, there are two parts to the phase. Phase 1 is the wave number, K2, multiplied by the total distance, which is, as you can see, AB, plus along the hypotenuse of a triangle, BC, and then to CD. And remember what the indices of refraction mean. C over N, in this case N2, is the speed inside the middle layer, and that's equal to omega over K2. That's one component to the phase. The other component is any phase change that's caused by the reflection coefficient phase when you're supercritical, either at this interface or at the upper interface. And so we have to add the phases from the bottom reflection and the top reflection to the, if you like, travel phase, K2 times the distance we need to travel. Now, let's see how we proceed. First, let's calculate the travel path A, B, C, D. We're going to make it easy for ourselves because what we're going to do is we're going to note that the part of the wavefront AB is the ray rather, here this part of the ray AB and this part DE are the same because this wavefront AD is moving parallel to itself down to the position BE. So rather than computing this little bit here, we're just going to put it over here and then compute BC to CE. And that's what I have there. I say the travel path, ABCD, is BCE. So let's start from the beginning. Let's look at BC. Well, first of all, you can see right here from B to the top of my pen, that's the thickness of the guide, H1. And by simple geometry, we can see that BC is just H1 divided by the cosine of theta. So there's part of our problem. What's left is CE. Well, CE, what we can see is we've got BC there. And this angle is theta, and this angle is theta. And we know what that is. We just calculated it. And now we've got to go down to E. Well, this is a right-angled triangle here. And we do know what this is. We do know what BC is. So you can see that this part here, CE, is just as written, BC times cos of 2 theta, which we write using a trig identity for cosine of 2 theta. Then we add the two together as shown in the last line of the equations, and bingo, we've got the travel path, BCE, 2h1 cosine theta. So let's continue on and calculate the phase. Now, we're complicating things a little bit when we have the boundary between two dielectric materials, N2 and N1 here, and N2 and N1 here. And so we're going to simplify the calculation in this case and pretend that there's a very thin metallic layer at each boundary, and that the electric field is going in and out, so it's purely tangential. When that's the case, we know from class that there is no tangential electric field on a conductor. It must vanish, and therefore there's a phase change at the bottom of 180 degrees and the same at the top, so the two are equal. Now, to compute the total phase, we have to add the travel phase, which is the distance 2h1 cos theta times k2 plus 2 pi. That's total phase for constructive interference. That's got to equal 2m pi, where m is an integer. So therefore, we can solve by dividing, canceling out the 2's for k2 cos theta. Simple algebra. It's p pi over h1, and p is a positive integer. It's equal to m minus 1. Okay, so we have phase 1, travel phase, phase 2, the phase due to the dynamics of reflection. The total phase, as we just saw, was 2m pi. Let's see where this takes us in terms of the implications of this constructive interference condition. Recall that k2 cos theta is the x component of our wave number, k2. Now, it's the component here. So in much of the literature, you'll talk about this method as the transverse matching method or the transverse phase construction method. And we've come up with it straight geometrically to get the basic idea. Now, let's rewrite our interference condition simply as kx is equal to p pi over h1. Remember, kx is k2 cosine theta. Kx is the x component of the wave number k2, which has a value, scalar value, omega divided by the speed, which is c over n2. Furthermore, we know that we can compute the magnitude squared of k2 as the sums of the squares of kx squared and kz squared. Straight Pythagoras. Now it's a bit of algebra that comes to the end of this whole discussion. Simply solve for kz, which we've done. So we have kx here, and we substitute our matching conditions for constructive interference here, and we get a result for kz. Kz saying that the energy, the wave has a component along the guide, so the energy is carried in the positive z direction. I noticed that I picked the positive sign of the square root. Now, look at kz. As long as kz is greater than 0, that means we have movement down the guide of energy down the guide. However, Look at the conclusion. If you fix P is essentially the number of wiggles we can fit between the plates, the mode, and you fix the geometry of the guide width, or height in this case h1, then we can choose an omega here so that kz vanishes. If we choose omega low enough, the difference between the quantities in the square root will be 0, and kz will vanish, and there will be no energy propagation down the guide. And that frequency is called omega cutoff. So the guide acts as a filter. If the frequency is too low, no energy goes down the guide. Given this, we can solve for the amplitudes, and I do that in the notes in edX. And then we have a complete description and a lot of intuition based on this analysis as how a waveguide works.